we're going to spend the first few minutes here just reminding ourselves of several things. What does it conceptually mean, big picture, to be an inverse? How do I look at equations or ordered pairs and find inverses? And then graphically, what does that mean? So when I use the word inverse, what does that mean to you? What's that? Okay, so I hear the word opposite. We're going to change that wording a little bit, but what do you mean? Explain. Okay, I like that. That's on the right track. What else does it mean to you? Anyone remember why we need an inverse? Not even just trig. Like, why do we need an inverse in general? Instead of doing this first slide, let's start the conversation here. When I have y equals x squared, why would I need an inverse? Yeah, Ryan?
So you can find the original input if you only have the output.
So that I can undo an output to find an input. The idea of y equals x squared is one of the first places in mathematics where you learn why an inverse is needed. So you learn things like, hey, I can quickly sketch the graph of this quadratic, and I can think about this function in terms of ordered pairs. So for example, I can say find the square of 0 is 0, 1 squared is 1, 2 squared is 4. Going the other way, negative 1 is 1, and negative 2 squared is 4. But when we start to think about how do I undo a square, you could give me a function. How do I undo a square? I square root. If you think about it, if you think just solely based on what Ryan just said, if we talk about the inverse, then I need to be able to put in 4 and get out 2. I need to be able to put in 1 and get 1. I need to be able to put in 0 and get 0. A better example that would further the table, I need to put in 9 and get what? 3. I need to have a function that when I square it gives me 9, but when its inverse inputs 9, I get 3 out. Ben?
What would you do for the numbers that are negative on the top?
Great question. So we got to think through some of that. So technically, by ordered pair switching, right, that idea of an inverse where I put in the output and get out the input, that's what it would look like, ordered pairwise. Same thing here, I would put in 4 and I would get negative 2 according to these ordered pairs. But what would be the problem with that table the way it is right now? It's not a function. So what we do, because of situations like this and this, where my input yields 2 outputs, I still need that inverse function. I still need to be able to input 4, 9, 16, 25, 42.7, and get the outputs that are what the original was being squared to give me my input here. I need to be able to put in 16 and get an output of 4. So what we do is several things. First of all, we have to define the function. So do you remember how it works when I have y equals x squared? How do I find the inverse? I flip x and y, which would give me x equals y squared. And then I what? As is, that would be poor form. Solve for y. So how would I solve for y? Square root. So I'm going to square root here and square root here. So I get y, and technically I get plus or minus the square root of x. But because of what we just said, that yields a table in which my inputs would yield more than one output. We do what's referred to as we restrict the domain. Does that sound familiar? We restrict the domain so that I look at all the values of the range. I have to be able to put in any number that has been squared. And I take all of those values of the range, but I take just the part that does what? Why would I just take that part? Why would I not go over here? what would happen the second I started to include those? I just can't hear you. When I flip the points, it would not be a function. What's that called? How can I look at this portion here? How can I look at that original graph and say, you know what, I can only take from this to this so that its inverse will be a function. It must what? You remember, Eric?
Well, I was going to ask, why does it matter if it's a function?
Mostly for practical purposes. Like, generally speaking, and this is true mostly especially when we go into real-world situations, okay? So in real-world situations, you can't have multiple outputs, especially when that results in confusion of an idea. So just by general rules of mathematics, you want to create an inverse that is a function. Now, does it have to be? No. So we would sometimes say that in reality, the inverse is not a function. That's the phrase that's used when you're first taught this. So when you plot these, for example, you would have 4, 2, and 4, -2, right? This would be the picture of my inverse. The only thing is, for practical purposes, when I go to solve, I can't be getting 2 outputs because of just general rules of mathematics. Your output has to come from a function. So some of your answer is just, that's the rules of mathematics. Okay? The truth is that we also are sophisticated enough that we can say, well, it's just not a function. So why can't you still get 2 outputs, which I think is what you're saying, right? I don't totally disagree with you, other than it's just poor form from like a mathematics sophisticated perspective. Okay, so what portion how are we going to decide what portion to take? And why can I not just take a chunk of this red? There are key phrases that I'm listening for. What's that? What's that mean? I just can't tell what you're saying.
I don't know.
I actually like what I think, but I just don't know what you mean by adjacent. Okay, so I like that. So he's saying take the positive. I would say you take the positive portion because typically when we take the square root, we would say you cannot take the square root. You have to get outputs that are positive, right? It mostly just by, again, that same idea of hierarchy of mathematics when we make those decisions. Okay, yeah, Chloe. Yeah, for sure. Okay, so what else? Why else did I choose that section? And why could this section not have gone into this part over here? You should. The second I try to include this, that should bother you. I don't disagree. Okay, when you square root a negative, you can't get a negative, or we square root a number, you can't get a negative out. Right? I agree with that. You should remember phrases like this. Start to jot this down. We must pick a portion of the original that passes the horizontal line test. I must pick a portion of the original that includes all the values of the range. Typically, not always, but typically, and especially in this case, I include originals that are in the first quadrant. I don't have to, but I try. So when I go to say, what is my output here, I don't say y equals positive or negative square root of x. I simply say my inverse is y equals the square root of x. I would also remind you that from the original, and I'll get your question, Andrew. From the original here in red, when I take just that portion and I reflect it, do you remember the rules? The new graph will reflect about what? Yeah, it will reflect about y equals x. So what's there in black is the original restricted domain that then reflects about the line y equals x. Yeah, Andrew?
When you say that we're supposed to try to get it in the first quadrant, if it's like on a test and we have the option of choosing the first quadrant over the second quadrant, and we put it in the second quadrant, are you going to take marks off for that?
On the Trig stuff, yeah. But you'll see why here in a minute. It'll make more sense. Ben?
What does that mean, this first quadrant?
Well, so see how this, like, this original portion, I choose that as opposed to that. Right? Does that make more sense? Okay. Okay, so let's go back now and consider these. For example, how do we take y equals 3x minus 5 and find the inverse? What would I do based on all the conversation we just had? Swap x and y in. Solve for y. Who needs 30 seconds to finish that? Okay, good. So let's do that real quick. This is x plus 5 all over 3. That's my y, yes? Okay. What about if I just gave you ordered pairs? What if I ask for the inverse of this set of ordered pairs? What do I physically do? I just take those ordered pairs and what them? Yep, flip them. 4, 2, 5, 1, 8, 0, 4, 3, 0, 4, and 8, 5. And then in number 3, I can go through this process again, but I want you to see what we did. When we started to look at this last year, and we needed to solve for y, we ended up creating a function. Do you remember what the name of the function was that we created? How do I get a variable out of the exponent? I have to use logs. So similar to what we're about to do, at times someone comes along and says, look, this is the inverse function that's going to undo my original. So I can get y by itself by saying this is log of x base 2. This is my inverse. Graphically, how do I consider an inverse? From an original to the inverse, what did we just say? It does what? Yeah, x becomes y and y becomes x, and it reflects about the line y equals x. So to do this one, I want you, with whoever you're working with, real quickly, come up with these 4 ordered pairs, and then come up with their inverse points, and then we're going to graph it together. Go. Go ahead, Ben. What's up? Yeah. Okay, so take 30 seconds to do this. So this is the inverse. So this 2 to the y equals x is the same thing. It just gets y by itself. Okay. Well, from here to here, these two are the exact same expression, but this is just negative 8. And this is y by itself. Yeah, but that's the original. 3 is off of the swap x line. Yeah, but that's just taking, that's like exponential.
What?
This, right? So the inverse itself is actually just 2.
Oh, that's good.
It's just to say the inverse without saying y by itself. So just swap it so that you then have y by itself. So by definition, this is the same. Yeah. Okay, can I get someone to rattle off those 4 ordered pairs, please? McKinley, will you give me the honors?
I got -1, 8. Well, wait, is this the original?
The original.
Okay, then 8, -1.
Okay.
3, 4.
3.
Zero.
Wait. You mean negative 3, 4?
Yes, that's
Yes.
exactly what I meant.
Okay.
0, 1.
Yep.
And then 8, -3.
Okay. Got it? Sophie, what are the inverse points then?
-1, 8.
Yep.
4, -3, 1, 0, and then -4.
Okay. So now I'm going to plot these. Again, as a reminder, you should notice that the original and the inverse reflect about y equals x. So I take these 4 key points because these are where the picture of the graph changes. So I start with -1, 8, which is up here. 4, -3. 1, 2, 3, 4, -3, which is here. So what I like to do is, since that's these 2, I'm I'm going to connect these dots. Again, you can already see how this is reflecting. Yep.
-8, -1.
Yep. Thank you. There we go. Thank you. So -1 and -8. Sorry about that. And 4, -3. There we go. Then we've got 1, 0, and this is where we got to be really careful. So I've got this point here, but this section is curved, so this section will also be curved. I'd also argue that you could list this one, even though I didn't say you had to, as -1, 0, which would mean this would actually come down here at 0, -1. Then we've got -3, 8, which is up in here, and this connects. Now, what you should be able to see, even though it's not proportionally perfect, is that my original and the inverse are reflecting about y equals x. So with all of that conversation in mind, we're going to look at y equals cosine of x. And we're going to start to talk about some of the characteristics as to why we need its inverse. So as a reminder, what do I take the cosine of? What are my inputs? I take the cosine of, throw something out there. I need it louder. What do I take the cosine of? In my head, this is all I hear. It's like right here. What do I take the cosine of? Give me an example. Cosine of pi over 2. Give me another example. 2 pi. Give me another example. True. Can we be more specific? Cosine of?
3.
We could, but that's weird. Cosine of what else? Throw things out. Keep going. Okay, what are those? I'm taking the cosine of a radian or a degree, some sort of angle. So I, for cosine, have inputs that are angles. We're going to refer to my outputs as my trig ratios. So when I think about an inverse, I need an inverse so that I can input a trig ratio and I can output an angle. I need to be able to say, hey, what's the inverse cosine of -1/2 and get out an answer. So we start to go through the process and we say, okay, well, let's go ahead and do what we just did. Let's go ahead and reflect about the line y equals x. So here's my original cosine. And when you reflect, you literally take this and reflect about the line y equals x. Here's my answer. Well, clearly, what's the problem? What's the problem when I go to reflect the red to get the blue? I'm sure you're saying something wise, but I prefer not to call on people, but if I can't hear you, I'm going to be forced to call on people. Tell me what you notice per our previous conversation about y equals x squared. Why is the blue a problem? The original does not pass the horizontal line test, so when I reflect it, the blue doesn't pass the vertical line test. As is, the inverse cosine is miserably not a function in infinitely many places. Yeah, Jasper?
So how do you know it doesn't pass the horizontal line?
Because literally, when, on the red, when I take a horizontal line and place it on that graph, how many times is the horizontal line going to hit it? Yeah, infinitely many, right? So when I go and reflect all those points, how many times is the vertical line going to hit it? Infinitely many. And in order to be a function, you have to pass the vertical line test. One input leads to one output. Okay? So what we need to then do is follow similar steps to create an inverse that is a function, to make sure I include all the values of the range, to include that first quadrant. So we're going to start to look at sections of cosine. So can you I'm going to ask you in a minute to talk with your partner close by. I want you to look at closely cosine. What section, find a section that would include all the values of the range, that's continuous, that is one chunk. Find a section that includes the first quadrant. Find a section that passes the horizontal line test. And by section, I mean from this x value to that x value. Okay, just real quickly pair up. Can you name a section that does those things? Go.
There's in a section
Okay, I'm hearing it all over the place. First quadrant passes the horizontal line test, includes all the values of the range, and is continuous. Say it. From 0 to pi. Okay, so I want to start to clarify. There are 4 rules, so write them down. I need to choose a section that includes all the values of the range. It needs to be continuous. It needs to include the first quadrant, and it must pass the horizontal line test, otherwise the inverse will not be a function. So a bunch of people are saying, hey look, from 0 to pi, that does it. I totally agree. So now we've got to create that inverse. So to do that, we're going to start to look at x and y values. So first, my input for cosine is an angle. So let's run it from 0 to pi. Let's do 0. Let's do, just to keep it a little interesting, pi over 4, pi over 2, 3 pi over 4, and pi. Okay, so you're going to find those y values for cosine. Then you're going to create those inverse points. You're going to physically do what with these ordered pairs right here? Flip them. Okay, go. Yeah.
When you say like it's in the first quadrant,
It just has to include the first quadrant. So, for example, we don't want to do this section.
well, I was thinking like 0 to pi root 2, because that's just the first.
Totally agree, except then you don't hit all the values of the range. So if I were to say what's the inverse of, the cosine inverse of negative root 3 over 2, you wouldn't be able to get that out. Okay. Okay, so you'll notice we're putting our last couple of quick quizzes on hold just so that I can get you to a point where it'll be most useful. So, but these are values that could easily be on your quick quiz. What is the cosine of 0? Let's do this fast. Come on. Cosine of 0 is? 1. Pi over 4. Root 2 over 2. Pi over 2. 0. 3 pi over 4. Negative root 2 over 2. And pi is negative 1. Now I'm going to physically flip these. So, and again, jot these notes down. On my original, my input is a domain. Sorry, that was a weird word. My input is an angle, and my output is a trig ratio. So when I take that inverse, now what's being inputted, I don't think that's really a word, is my trig ratio, and what's being outputted is my angle. So I physically just flip-flop these. I input 1, and what do I get? 0. I input root 2 over 2, and what do I get? Pi over 4. I input 0. I get pi over 2. I input negative root 2 over 2, and I get 3 pi over 4. And I input negative 1, and I get pi. So now I'm going to blow this up so you can watch. We're going to graph this. And I want you to physically see how this plays out. I'm going to look at this section of cosine. That's the portion that I'm reflecting. So when I look at the point 1, 0, here's 1.57, otherwise known as pi over 2. 1 is somewhere in here. There's my 1, 0. Notice this distance and that distance are about the same. Then I have root 2 over 2, that's 0.707, and pi over 4. Now keep in mind, I've been really pushing this decimal understanding. Anyone got their calculator out? Jasper, will you type in pi over 4, please? Okay, so 0.7. So this is essentially 0.7-ish, 0.7-ish. So I'm going to go over a little less and up a little less. 0.7, 0.7. This is 0 pi over 2. So that is 1.57. So I've got this up in here. You can see how this is taking on this curve. You can already see how it's reflecting. This is negative 0.7. Jasper, will you type in 3 pi over 4 for me? So notice I'm starting to curve up. This is coming up like this. And the last one there is negative 1 pi. So I am up in here, and it's going to hit up here. So I've got this curve. And if you look, if you've done a decent job, this curve here should look like this curve there. So take a minute and try to get a pretty reasonable picture. When I look at this, I can see that it's reflecting about the line y equals x. Okay, now, what I want you to begin to understand is this comparison. So I'm going to zoom this way back. And I want you to understand that we are comparing the original cosine to what we're going to refer to in this green graph as the inverse cosine of x. We use what looks like a negative 1 as an exponent. It is not an exponent. It is a notation to indicate inverse. And what we're saying is I have an inverse cosine function that's the inverse of just cosine based on the interval 0 to pi. What this practically means is that I can input a trig ratio and output an angle. So for the last 10 minutes, we're going to look at the practical side of inverse cosine only. So, skip until you get to this slide. So, tonight's homework is going to be limited in scope simply because we're going to just highlight cosine. For no other particular reason than that's what we decided on first. You should.
I've got something similar that's a C.
Have like a yeah, that's not like
Okay, jump to the back where there's a blank page, okay? And write down inverse cosine of root 3 over 2. Okay, so this is the most basic, just go to the back, right?
I'm missing a bunch of pages. I don't even have a blank on the back. No.
Let's see. Got it? Thanks. There you go.
I guess I got it.
Okay. Inverse cosine of root 3 over 2 is the most basic question I can ask off this conversation. So first of all, let's remember that what did we say my inverse is representing? The inverse of a what? What is this? Thank you. Very good. It is a trig ratio. I have a trig ratio. Okay, so the deal is I now need to output a what? An angle. Okay, think unit circle. What values kick out, what angles kick out a cosine of root 3 over 2? Might take a second. Little louder? Yes, agreed, 30 degrees. Now, how many are there technically? Infinitely many, right? But we're not looking at infinitely many. We're only considering the ones that are where? From what to what? 0 to pi. Very good. So 30 degrees, we're going to call this pi over 6. Technically, could you list infinitely many? Not for a question like this, because this is simply saying evaluate. Evaluate says one input leads to one output. So when I look at, let's look at this for number 4, which you're just going to write down. I've got the inverse cosine of negative root 2 over 2. Okay, so this is a trig ratio. So I'm taking the inverse cosine of this trig ratio. I need to output the angle. What angle creates a cosine of negative root 2 over 2? You can actually look at our chart. We just did this. Oh, Brandon said the 45-degree angle over here. Could we be specific about that? 135, give it to me in radians. Well, 135 degrees is degrees. Give it to me in radians. Very good. 3 times 4. Technically, how many answers would there be to something like that? Technically, infinitely many. But the second we define it as a function that is an inverse, one input can only lead to what? One output. One input can only lead to what? Say it again. One output. And that output must be between what and what? 0 and pi. Okay. So now, you might just be missing that slide. Let's make it a little more sophisticated. Look at number 2. This you have. I'm not sure why you're missing just that slide. This says the cosine of the inverse cosine of root 3 over 2. So what do you think I'm going to have to do first? We're going to work inside out. If you need to, circle that and write that phrase. We're going to work inside out. It's not terribly different than PEMDAS. I go inside the parentheses first. What is the inverse cosine of root 3 over 2? We just did it. Yeah, pi over 6. What is the cosine of pi over 6? Root 3 over 2. Why does that make sense? Yeah, say it a little louder, Andrew. Yeah, basically, I'm sticking in something that gets the output that gave the first thing to begin with. Now, what we're going to explore tomorrow is, will that always be true? But here's a little preview to it. Look at the inverse cosine of the cosine of 7 pi over 6. Where do we start? Inside. What is the cosine of 7 pi over 6? Negative root 3 over 2. What is the inverse cosine of negative root 3 over 2? I think you're starting to say it. What angle, this is a trig ratio, what angle causes that trig ratio? 150. Why didn't Brandon just say, which is, what are those radians, by the way? There we go, 5 pi over 6. Why couldn't Brandon just say 7 pi over 6? Why couldn't he just kick that answer right back out? We just kicked that answer right back out there. June? It has to be between 0 and pi. Okay, so let's look at your homework. And we're just going to start on this. And, yeah, we'll just keep it simple for tonight. Couple things that I just want to comment on. First of all, eventually you're going to decode a message. I realize that sounds super exciting. So, on the side that says the problems, do you see them? On the side that says the problems. Tonight, you're going to keep it really simple, and you're just going to do everything that says cosine. So, for example, number 4, number 5, and number 6. Now, in the meantime, that's going to sound a little weird, so I'm going to also hand this out to you. And you're going to do the cosines on this as well. Okay, but I want to introduce you in the last 3 minutes here to one other notation. So on Schoology, I will say cosine problems only for worksheets 9 and 10. And I want to just highlight what you will be exposed to along the way. When I talk about the idea of y equals inverse cosine of x, someone came along and said, hey, I think we might need a better notation that does not include this exponent. So they replaced it with what we call arc cosine. This idea of arc is replacing that notation for the -1. So know that when I look at number 5, it says arc cosine, that's just the inverse cosine of 2. When I look on other sheets, for example on worksheet 10, when I see arc tangent or other arcs, that just simply means inverse instead. Now, I expect this to take you all of like 5 minutes. I don't expect you to even totally know how to do this well. By tomorrow, you're going to know how to do a lot of it. Okay? But we had to introduce all of this. Yeah, and honestly, it will take you minutes at most. Okay? Okay, that's it. Have a good rest of your day. Hey, if you did not take the quiz yesterday, will you come see me?
That's the. I forgot I was supposed to show you after class.
Hang on.
Hmm?
Hold on a second.